It was a pleasure to be back in Toronto. I've been gone for about 37 years, and I'm actually thinking about staying, but it's always a pleasure to come back. And so I've given this talk a title of Sustainable Energy Generation, Distribution, and Security. If you give me another 10 minutes, I'll change the title, be something different, but that's probably somewhat accurate. And I'm going to talk about energy, but I'm also going to talk about the inventive process and try to give you some insights into how I go about solving problems, and maybe there's some takeaway messages for everybody. The subtitle could be Liquid Metal Battery Cost-Based Discovery, and that's really an important step right there. Most of my colleagues in the university are focused on inventing the coolest chemistry. And when there's an orthogonal path in the road, one direction is build a career and the other one is solve societal problems. And most academics are building careers. So that means piling up the Hirsch factor and getting lots of refereed journal publications. But the problems that are facing society have a cost associated with them. And it's my thesis that when it comes to energy-related problems, you can't invent cool chemistry and then expect that when the product gets to the manufacturing phase that the costs will come down. We see that with lithium-ion batteries. It's 20-year-old technology. It's still way too expensive. And even with full measure given to the gigafactory, it's not going to have the impact that is needed to get your arms around stationary storage, no matter what people say. So my approach is start thinking about cost on day one, not on day 1001. And that's different. So that's changed the way I do research. I'll show you what I mean. But knowing that I was coming to H.H. Angus, I wanted to be a little bit canonical and professorial too. So I asked myself, what is an engineer? And of course, growing up in Canada, I know the first place I look is the Oxford English Dictionary. And one of the versions of the OED defines the engineer as one who contrives, designs, or invents. That invent piece is really important. That's what an engineer is. And this is from 1325. It's in Old English, but I think it's fuzzy enough that you can figure it out. A tower full strong that quaintly engineers made. Quaint used to mean elegant, and then by the 18th century it started to take on a meaning of sort of, that's cute, but it's not really important. But there it is. The engineers were doing this. It turns out that the word engineer and ingenious, both those words have the same root. And I like this comparison. A scientist discovers that which exists, an engineer creates that which never was. So that's the creative thing. And don't misunderstand me, I don't disparage science. I'm a big supporter of science for science's sake because we need that basic knowledge. But what distresses me is not that there are people in the School of Science pursuing science. What distresses me is that there are people in the School of Engineering who are not inventing. If the people in the School of Science are doing math and the people in the School of Engineering are doing science, who's doing engineering? This is von Karman. But I was at Corning the year before last at their patent banquet, and one of their scientists gave me this tidbit. Scientist converts money into ideas, and the engineer converts ideas into money. Very nice. So now let's get to electricity. Why do I care about electricity? Because for me, electricity is modernity, and it's never been more the case. If you think about what is the most remarkable engineering achievement of the 20th century, it's the grid. Electrification of the country was the #1 priority to modernization, and it remains such. And when you take a look at this image, you can see where people are participating in the modern world. Everything you have, all of your devices, information, this talk and everything, it's all brought to you by electricity. All the thermal energy in the world isn't going to get you there. And there are dark spots on this map. By the way, you know this is a collage, right? This is not the world by night, because when it's dark here, it's light here. You know? Now, there are some audiences, when I show this, they say, no, that's NASA picture, that's the world at night. No, it's not. If the world ever looks like this at night, it's a bad day. It's a really bad day. Now, there are parts of this where it's dark, and it's dark for one of two reasons. Either nobody lives there, or it hasn't been electrified. The 2 out of 7 people on the planet don't have access to electricity. Now, one of my, as you know, I'm very passionate as an educator, and I have a very low opinion of massively online courses. And that's very unfashionable to say it, because at MIT there's a whole bunch of colleagues, and there's a big initiative on MOOCs. And to me, this is just a sleight of hand, because they talk about how with these MOOCs, you can get access to an education in a way that allows a poor child in Africa to get an insight into an MIT classroom. And I'm saying, no, it can't. It doesn't have access to electricity. If you don't have electricity, you don't have access to anything. If you have electricity, you have access to ability to purify water, which means you've got health, which means you can start to think about other than survival, which means that you can educate yourself and get information streaming in. So the key to poverty is electricity. That's why I work on this. And the way to get electricity here is not to string it up to a line here. It's to put a solar panel here and just, you know, like China doesn't have telephone cables all over. They just leapfrogged over. Everybody's got a phone and there's a satellite up there somewhere. Don't need the copper. So let's think about how we're going to leapfrog over this. So, we've heard about storage as an enabler, but I want to point out that it's not just an enabler in the case of the intermittency of renewables. It massively reduces investment in today's grid. I mean, today's grid is absurd. You know, the electricity powering the lights in this room was generated just moments ago, because the grid is this gigantic delivery system, supply chain with zero inventory. So that means if I want it, it's got to be generated. If it's generated, nobody wants it. It can't just go somewhere. It will interact and it will disturb you. You assume that you're getting 60 cycle out of that wall socket, and it's 60 cycle plus or minus a fraction of a percent. If the supply and demand get out of balance by more than a certain degree, the frequency will migrate. And you know, you go to a place like Afghanistan and Iraq, the problem isn't that the power is off. The problem is that when the power is on, it might be 48 cycle, it might be 55 cycle. Can you imagine if every time you went to plug in your device, you're going, do you feel lucky? Because that could be blowing up the devices. So we have a mandate on the grid that we're ready for it, the peak load. The peak load occurs a few days in July and August. And the rest of the time, it's just humming along. And that means typically in the first world, it's about a 40% differential. In some cases, 50% differential. Now, imagine if you had to build a Gardner Expressway so that at any time, none of you would ever have to tap the brake pedal. It would be 20 lanes wide in each direction. And you'd say that's insane, that's wasteful, but that's the way we demand the grid to be. It's 20 lanes wide in both directions at all times. Now, to electrify the world, international organizations have estimated that it'll be about $17 trillion over the next 20 years. And if that's a 40% excess doing nothing, that's $7 trillion that's just wasted. That could go into healthcare, could go into education, and so on. And then, of course, renewables. Renewables, because of their intermittency, are useless. If they don't contribute a base load, they don't help. It's not as though, well, I've got some solar in the middle of the afternoon, let's contribute. It's not a contribution. It ruins the balance between supply and demand. So it's no good. And you know, when you drive a car, what's the best way to drive that car in terms of energy consumption and emissions? Get it up to highway speed and hold it there. You get the most gas mileage and the fewest emissions per unit distance driven. What's the worst thing you can do to drive a car? Accelerate from rest, hit the brakes, accelerate from rest, hit the brakes. So what do? When the solar comes on, and the mandate is that if there's renewable energy, the ISO has to ship it ahead of anybody else. So we call the coal plant or the nuclear plant, and we say, we need you to ramp down by 5% because we've just got some wind or solar coming into the grid. Oh, now the clouds are coming. Oh, the wind has stopped. Now we need you to ramp up again. Oh, now we need you to ramp down. Now we need you to ramp up. Well, wouldn't it have been better to just take coal to the sweet spot and hold it there? But, you know, this is complicated. You imagine, you know, the general public doesn't understand this. They think it's a contribution, but it doesn't work that way. The grid doesn't work that way. Imagine if every time you want to take a shower, first thing you got to do is see if it's raining, because there is no ability to collect water. It's supply and demand. Very different. And there are all kinds, I mean, people talk about the grid as this one electrical need, but it's so complicated. Here's one example. Places in New York, there's a spur that goes out, I can't remember if it's Queens or Brooklyn. They got plenty of electricity in the greater New York area, but not on the island of Manhattan. The way the grid is organized, you've got to go from this one central spur out. They're coming up against the limit of the transmission line, and the demand keeps growing. You say, well, just put in a new line. $1 billion. Now, who's going to pay for that? You see, if we decided to form an oil company in this room right now, we could have this one company explore, drill, pump, ship, refine, make product, and sell retail to the customer, the vertical integration. But in the electricity market, the people who generate it aren't the people who ship it. The people who transmit it aren't the people who sell to the ratepayer. And so when everybody's standing there looking at, wow, that transmission line's going to need some upgrade, everybody stands back. It's like it's at the dinner table, and everybody's wondering who's going to pick up the check, you know? But in the end, it doesn't matter. Guess who's going to pay for it? The ratepayer. So transmission line deferral could be avoided by storage, so that in the wee hours of the morning, you just continue to send electricity, store it where it needs to be, and that way avoid these new transmission lines. There are high pain points like the Hawaiian Islands. They import diesel, burn diesel. Their costs are, round numbers, 40 cents a kilowatt hour. They're the highest in the United States. They got sun and wind in superabundance. So they're willing to pay a lot more than somebody is, say, in Ontario. And there's security. You know, right now, I see there are a few young people here, but I think most of us remember August 2003, tree falls in Ohio, and minutes later, 55 million people across the Northeast are without electricity. Why? Because the whole thing is interdependent. It's absurd. A tree falls in Ohio and you don't have electricity here. What's that all about? So the antidote to that is to decentralize the system. And it's a decentralization of electrical power. It's a decentralization of power, which I tend to favor both. And then there's some non-technical factors. The grid's aging. We're right on the edge. I mean, there are spots of the grid that are just really, really rickety. Boston had the worst winter. I've been there 37 years, and I grew up in Toronto, so I know what winters can be. But this winter in Boston exposed the weakness of the decaying infrastructure. And we're not far from that in other parts of North America. So replacing those plants would be a lot easier to put in storage, keep those things going. Rooftop photovoltaic, all of that stuff. I can hear everybody talking about decreasing the cost of photovoltaics, but if they're not part of base load, they're not a solution. And it's funny, you go to somebody at MIT who's working in photovoltaics, and they'll say, oh yeah, no question, storage is the big obstacle. So what are you working on? Well, this is really new material that we can get a 1% increase in conversion efficiency. And I'm saying, suppose I gave you 100% conversion efficiency. What happens after dark? Silence. This is not glamorous. And the demand charges. I mean, this, again, the public doesn't get it. They think it's like toilet paper. If you buy 1 roll, it's X. If you buy 10 rolls, it's less than 10X. But in electricity, if you buy X and then you buy 10X and your allocation is 10, if you buy 11, you pay not more for the delta, you pay more for everything. You just bumped yourself up into a big, big penalty for the whole month because the grid operator is counting on you never exceeding a certain value. So now you're looking around and you're saying, wow, business is booming, but I'm about to bang up against the demand limit. Do I shut down an assembly line? Do I send workers home? Or do I just pay the obscene charges? Or do I call one of my neighbors and get into a demand response kind of a situation? That's the kind of complexity you get into. Well, if you had storage, you just have your own. Well, this graph shows installed capacity as a function of capital cost, and it's a log plot. So this is 1,000 times. This is less than 0.1%, so it amounts to nothing. So none of this means anything. The other thing I learned about this is that pumped hydro seems to work, and it's way up here, and the rest of these don't work at all. And the other thing is, if I don't get down below $500 a kilowatt hour, I'm wasting my time. So there are real metrics here. This is what I mean by cost-based discovery. If I give you something that gives you 5 times the energy density of lithium ion at $2,000 a kilowatt hour, so what? It's really cool to a NASA price point. It's useless. So where are we going to go? We're going to go to the university. Why? This is the origin of the battery. Professor Alessandro Volta at the university. He gave birth to this field of electrochemistry. This is his first battery, a stack of coins, silver and zinc, separated by cardboard soaked in brine. And with it, he gave birth not only to the field of electrochemistry, but almost immediately technology, electroplating, electroforming, and this laid the groundwork for, with the invention of the dynamo, came electrometallurgy. It all started at a university. And so Volta actually did 2 things. He gave us this new field, and with his invention of the battery, he, for the first time, demonstrated the utility of a professor. See, until Volta, nobody thought a professor would be of any use. But Volta showed that research on a university campus could be very powerful. You give a professor money and leave him alone. It's liable to come up with something that's really powerful. So let's talk about grid level storage. Why do we have it, and what am I doing about it? Well, first of all, I don't talk about battery versus battery, so don't ask me about somebody else's batteries because none of them are good enough. It's battery versus combustion, and that's a really tough one because combustion is, hydrocarbons, very energy dense. That's why we use them. We don't use them because they're being forced on us. The notion that in a liter of gasoline, you've got enough energy to take a vehicle weighing several tons miles down the highway, it's phenomenal. So how are we going to compete against that? Well, we've got to think differently from what we've been doing up until now. The people that design the batteries that go into this device are not going to win by taking this and multiplying all the dimensions by 1,000. That's what Boeing thinks they're going to put on the Dreamliners, to take a lithium-ion battery and just make it bigger. It doesn't work that way. I know, I'm an electrochemist. And today's lithium-ion batteries are way, way too costly. They're even too costly for automotive. And automotive has a higher price point than stationary. I'm always amused when people come to me and say, I got this business plan. We're going to take spent batteries out of cars and repurpose them for stationary storage. I'm thinking, that'd be great. Except that stationary has a lower price point than automotive. And you've just told me that the battery is spent as an automotive battery. So how are you going to take something that operates in a more expensive market, has now run its course, and put it in a lower price point? I don't know. Maybe somebody here knows the answer to that, but I can't explain that. But it sounds really good. So what is my approach? First of all, confine your chemistry to earth-abundant elements. So here's a plot of atomic concentration as a function of atomic number. And this was taken from a government publication. And why they connect the dots is beyond me, because there's lithium and there's beryllium. There's no element with an atomic mass of 3.4. So this is one of those times where you do not connect the dots. Let's connect the dots. And it's a logarithmic plot, semi-log, right? So that means these elements here are 1 billion times less abundant than these elements. So I can look at this and I can say, what is the relative size of the market versus the relative abundance? So for example, platinum is down here. It's about 1 billion times less abundant than aluminum. Now platinum's okay for the jewelry market, okay? But it's not okay for the automotive market. So that's why fuel cell vehicles are still in the future. And it always will be, because if you have to buy your electrodes at the jewelry store, so there's only one thing I would fund in fuel cell research. It would be non-noble metal catalyst. Because if you don't have that, it doesn't matter. If I gave you hydrogen for free, it doesn't matter. You don't have platinum. And by the way, do you think if the world demand for platinum went up by 100x, the price of platinum would fall? No, it's a constrained resource. Its price will go up. If the demand of steel goes up, the price of steel will go down because it's an unconstrained resource. The economics are very different. And by the way, there are a lot of people, including General Electric, that are spending money on cadmium telluride solar cells because they give higher conversion efficiency. And that may be true, I don't know, but even if it is, tellurium won't scale. Even if I gave it to you for free, it doesn't exist. Figure out how many square meters of solar cell you'd need. It doesn't exist. So what are you spending money on it for? It's a non-starter. So I look at this, and I look at the size of the energy market, and I forbid my students to work here. They are forbidden to go to this part of the periodic table because it won't scale. You got to build it out of here. If you want to make it dirt cheap, you make it out of dirt. And preferably dirt that's locally sourced. It doesn't make sense to trade in your dependence on imported neodymium for dependence on imported, your dependence on imported petroleum for your dependence on imported neodymium. So the problem should be turned around. You go in the backyard, bring a shovel full of dirt into the lab, and you say, invent the solution based on what's in that pile of dirt. Because I know when I'm done, it's going to be cheap, and I've got a secure supply chain. But people don't think that way because that's not the way the university works. The university works on cool publications. So right now, in materials science, it's all about graphene and carbon nanotubes. That's very, very nice. It's fascinating. But it's not dealing with the cost issue. And the second thing, it has to be easy to manufacture. It needs a primitive design. This is where the lithium-ion battery. You go to a lithium-ion battery plant. The gigafactory, why is it called the gigafactory? Because it's going to cost $5 gigadollars. $5 billion. Do you know what I could build for $5 billion? I could build a greenfield steelworks like Stelco or Dofasco, producing 250,000 tons per year of virgin metal. And what am I going to get? I'm going to get some 18650 cells. Yesterday's technology tomorrow, but efficiently made. So the cost will come down maybe 20%. But you need to get the cost down 2x, 3x. So when I started thinking about this problem about 10 years ago, I drew upon my experience in metallurgy. First thing is, I disregarded everything I knew about batteries because I knew that batteries were going to lead me down to the same dead end. So I looked at a modern aluminum smelter. And why? Well, aluminum smelter, you import bauxite from one corner of the globe. Carbon is a euphemism for petroleum coke. 13 kilowatt hours of electricity to make a kilogram of metal product. And the capital costs about $5,000 a ton. So you figure you got a smelter, it's 100,000 tons a year, $5,000 a ton. You figure out what the capital cost is of that. Dirt to metal for less than 50 cents a pound. And I said, that's an economic miracle. With all of this, you can still make metal for 50 cents a pound. So I said, how can I teach this thing? Because everybody else has got batteries like this that have lousy current capability. They're trying to teach them how to handle big current. I looked at this and I said, this thing loves current. Can I teach it how to store charge? Because I know if I can, it's going to be big. This is about, 20 meters, and that's about 2 kilometers going back. It was invented in 1886 simultaneously by Charles Martin Hall in the United States and Paul Héroul in France. They were both born in the same year, and they both died in the same year. And they met once, 1911, when Hall was given the Perkins Medal by the American Chemical Society, and Héroul came from France to the banquet, and he spoke in praise. They were both fierce competitors. Their patents ended up crossing at the World Court. But they had respect for each other, because that's the way the world was in those days. Not like today where they're tearing each other's eyes out, trying to win a Nobel Prize and sabotaging each other's data and falsifying results and so on. So this is Hall's patent from 1889. And I want to draw attention to the fact that it was aluminium back in 1889, even in North America. And that's not a typo, that the aluminium appears everywhere throughout that patent. Somewhere around World War I, it became aluminum in North America. It's been declared aluminium by the International Union of Pure and Applied Chemistry, so I'll call it aluminium. This is the French patent. Still written in script, and it's got lots of ribbons and big wax seals on it. This is procedure for the electrolytic preparation of aluminum. This is Paul Louis Toussaint Héroul. Yeah, there it is. And just to show you the difference, this is the Washington Monument, which was being built in 1876 for the American Centennial, and it was going to be capped by a pyramid weighing 100 ounces for 100 years of aluminium, because aluminium in 1876 cost more than silver. Aluminum is the third most abundant element in the Earth's crust, so when they invented this process for an abundant metal, they turned it from a costly precious metal into a common structural material. If this had been the process invented for rhodium, it wouldn't have made any difference. And by the way, The second most abundant element in the Earth's crust is silicon, which is the common semiconductor, and that's why we all have electronic devices in our hands, because they're made out of beach sand. And you know what's coming after electronics is photonics. Why? Because photonics are made out of silica, and that's silicon and oxygen, which are the first and second most abundant elements in the Earth's crust. So I know that photonics are coming because they're abundant, they're cheap, and they're everywhere. If photonics were based on cadmium telluride, they run a little network around Bell Labs, and that's it. You might ask yourself, by the way, with all those Nobel Prizes from Bell Labs, what impact all those Nobel Prizes had on the telephone system in North America? The answer is zero. Change to the telephone system came from outside the telephone industry. So now, instead of a precious metal on top, we have a beer can on top of the Washington Monument. So anyways, why is an aluminum cell not a battery? So I looked inside an aluminum cell, and I concluded it because we have fugitive emission of gas from one of the electrodes. So I said, well, maybe we could trap the gas, but it's an insulator, and then I thought about using sulfur and so on. Eventually I figured out we need to produce liquid metal at both electrodes. And so where am I going to get my metals? I got to go to the periodic table. And periodic table was enunciated by another professor. This is Mendeleev. He was 35 years of age when he enunciated this. And this is what he had to work with. These were the elements. Now, obviously, they've been arranged in periodic table format, but these were the elements that were known in 1869. And all he knew was things like melting points, boiling points, and he was the one that put them in order. And I have a theory. I've done a lot of reading on this, and he never confesses this, but I have a theory on it, that he used to travel by train, and he'd sit on his trunk in the station, and he'd play solitaire, patience, they call it in the old country. And it's my theory that because he played solitaire, and in his breast pocket he had file cards with all of the information. So you have lead, its atomic mass, its density, and so on and so forth. Every element had a little file card on it. And my theory is one day he's playing, he's got the ace of spades, the king of spades, and up comes the 10, and he goes, can't play the 10 because I'm missing the queen and the jack. And then he goes over here and he says, wait a minute. Arsenic is the next massive element after zinc, but it's more like phosphorus. I'm going to put under phosphorus, and I'm going to leave a blank here. And I'm going to put tin underneath silicon. And furthermore, I'm going to predict what's missing here. So he was a professor, and he was writing a book. And it was during the course of writing his chemistry book that he felt compelled to try to explain what's going on with the elements. And it was in the course of writing this that came this passage, which is he's saying, we're going to put them in rows into a table, and then here's the very many undiscovered members. Very many undiscovered members. He admits that this system is going to have a lot of blanks in it. So these are some of the elements that he said. Ika is Sanskrit for one. So one after boron, he said, will be here, and he predicted its atomic mass is 45, and it's 45, and he said Ika aluminum, which is gallium, and silicon, and which is germanium, and Ika zirconium. And then there's Ika and V. So it was one after and two after, and he predicted technetium and rhodium, and even predicted their atomic masses. And then this is the paper from 1869, published in Zeitschrift für Chemie in Leipzig. It's a little thing in German, and down here he's given the comments about how they're in order of atomic weight, and then later on, page 2, he talks about the missing elements and so on. So I go back to this table. That's all I have. It's actually a Canadian company, Permacharts. And when I was teaching freshman chemistry, I had hundreds of these. I'd give them out to my students. It's 2 pages of polymer laminate. This is on my desk in front of me all the time. I got my keyboard and the mouse goes all over this. Yeah. And so I'm looking at this. I didn't use quantum mechanics. I didn't use computational material science. I didn't use combinatorial chemistry. I sat and I looked at this. And I realized that if I want to get maximum voltage, I've got to take a really good electron donor and put it with a really bad electron donor. So I want to pair a really good metal with a really bad metal, but not a non-metal. Non-metal will give me gas. So something from the northwest part of the periodic table paired with something from the southeast part of the periodic table. And then we had some seed funds at MIT. You know, most of MIT has got nothing. They give you a desk and a name, and then you got to go and raise all of your own money. But they had a little bit of money starting in the mid-2000s in energy, and I had a little bit of seed money. And this was the first embodiment of liquid metal battery. So magnesium is in the top, antimony on the bottom, and molten salt in between. And they're separated by density. Magnesium is less than 2, antimony is greater than 6, and the molten salt is around 3. And magnesium is insoluble in salt, and salt's insoluble in antimony. So they phase separate like salad oil and vinegar. So there's no membranes, no separators. It's very easy. And magnesium wants to alloy with antimony, and so in order to do so, it becomes magnesium ion and sends electrons through the external circuit, and then magnesium alloys with antimony down here. So this layer gets thinner and this layer gets thicker. And then in order to recharge the battery, we force current through it and then electro-refine the magnesium back. So we restore everything. We restore the purity of the magnesium, the purity of the electrolyte. And there's none of the damage that you have in a positive electrode of a lithium-ion battery. And this operates at elevated temperatures. I mean, this melts at 650, this melts at 630. So the action of electric current generates joule heat. And that's what makes the Dreamliner catch fire. But here, I took that heat and turned it into an advantage and put brickwork around it and trapped that heat and used that heat to keep the battery at temperature. So it's autogenous. And so it's self-heating and way it goes. So earth abundant elements, you can argue about what's the relative abundance of antimony, but you know, I'm not working with platinum or tellurium. You know, this is, believe me, there are certain elements you don't have much of because they don't exist, others because they aren't in demand. This is because it's not in demand. There's plenty of it, don't worry. This is easy to manufacture. In fact, if you just pour salt and magnesium antimony alloy in the discharged state, just pour it in. If you want, you can put the metal on top of the salt, and when it melts, it flips over. It knows which way it's supposed to go. And I know some people are thinking, oh, he's crazy. He's going to lose all of his energy just keeping the thing at temperature. We have a round-trip efficiency after paying the thermal penalty of in excess of 75%, which is greater than the round-trip efficiency of pumped hydro. And I say this, and it doesn't matter. It just goes in one ear and out the other. And the naysayers come out and they say, it's crazy. He's losing all of his energy in just heating the battery and keeping it at temperature. No, I'm not. Round-trip efficiency is 75% today, and we've got some batteries in the lab that are over 85%. But I don't know. Energy, it's sort of, Edison said that when a man starts working on a secondary battery, it brings out his latent propensity to lie. Well, my observation is that when someone tries to work in the energy field, it brings out the most vicious critics. There is no support. Everybody feels obliged to eviscerate anybody who works in the field. So when you read criticism, that's just the norm. That's called commentary, you know? So anyways, we're doing all right. It's self-heating at commercial scale. It's immune to thermal runaway. If we want to use this as a load, we can shoot 1,000 milliamps per square centimeter through this thing, and the temperature will go up, but it doesn't catch fire. In fact, I had a couple of DARPA people with me once. They said, could you put this at a forward operating base in Afghanistan? I said, yeah. He said, so the Marines could put out their solar mats and they could have the, I said, yeah. He said, yeah, but wait a minute, what about a sniper? I said, what? He said, what if a sniper shoots a bullet into this? I said, well, it'll alloy with the magnesium or it'll alloy with the antimony. He said, yeah, but what about the metal's going to leak? I said, well, it'll start to leak and it'll freeze. They look at each other and they say, battle hardened. You know, you can't ship lithium-ion batteries by air. It's illegal. If it's happening, you hope you're not on that plane. But we went to the Department of Transportation, asked them what about our batteries, and they said, so describe what's the voltage at room temperature? Answer, open circuit. Oh, no problem. So you can ship these anywhere. Imagine a truck, two trucks collide on a highway, both going 120 clicks, flip over, and now you got salt on the road. Well, we need that. The question is it cost competitive for the electricity market? That's the only thing that counts. That's the only metric. So this is my team in summer 2007. This is David Bradwell. He was also born in Toronto. So two of us born in Toronto. He looks kind of worried because he was wondering if this thing's going to work. And I didn't tell him I wasn't sure it was going to work either, but I mentored him. How did I mentor him? I said, it's going to work. And he had a bachelor's in physics from Queens. Why is that important? He was not an electrochemist. I taught him electrochemistry. I taught him to think about the problem my way. So I brought the novice, not just the man off the street. He was intelligent, but he was not steeped in electrochemistry. And by the way, how did I learn chemistry? I learned chemistry by teaching. One of the things that I had as a bald spot in my education at the University of Toronto was chemistry. I was a graduate of engineering science, in material science, in the metallurgy department, and my knowledge of chemistry was abysmal. Why? Because metallurgists don't study chemistry. Why? Because iron is all made from iron oxide. Aluminum is all made from aluminum oxide. Magnesium is all made from magnesium chloride. So those pathways are set. So the first chemistry class is already thermodynamics. There's never going to be an exhaustive study of all iron mineralogy. The supply chain is fixed. The corollary to that is that the intellectual growth of metallurgists is stunted because they are not exposed to the basics of electronic structure and bonding. And I found myself at MIT, and the material science department had a class that satisfied the freshman chemistry requirement, and I ended up in that class. And I eventually assumed control of that class, and I had to teach myself chemistry. And when I did, I went through what Mendeleev went through. It was the best thing that happened to me. Worst thing that could have happened to me is I'd studied chemistry at the University of Toronto, because then I would have known that this thing couldn't possibly work. So here's David, and yeah, a couple of years ago, American Chemical Society was doing a profile on me. They asked for an image, so I sent them that, and they said, no, we can't use it. I said, why not? He said, well, you're not wearing safety glasses. I said, it's just a staged picture. This is just a, no, we will not show people in the laboratory dressed unprofessionally. I said, why don't you just take out a magic marker and put the things around? And they said no. So I had to get another picture. And then the MIT Energy Initiative was started, and I gave a talk in Paris, and they were, Total, big French energy company, asked me, what would it take? And I knew they were an oil company, so I blurted out a big number. And they gave me $4 million, and then I was a first round ARPA-E winner for that new division of the Department of Energy. So then I had $11 million, and this was my team by summer of 2010. And there are a mix of graduate students, postdocs, undergraduate students, multinational task force. She's from Spain, Korea, China, France, Trinidad. He's from French Polynesia. He was from Tahiti with a PhD in high energy physics in Paris, ends up in my lab. She's from Poland. David and I are both from Troy. David's smiling now, you can see. And I hired a few Americans as well. And again, the only person that was steeped in electrochemistry was me. And I was self-taught. These people were really bright, but they were not electrochemists. Because if I had a team of electrochemists, I would have had a bunch of people that would have just told me why this can't work. And by the way, with 20 people for 3 years, they worked miracles. So 20 times 3 is much greater than 3 times 20. If you gave me that same amount of money spread over 20 years with a group of 3 people, I wouldn't be standing here right now. So if you really want to deal with a critical problem, you put a critical mass on it. And you hire well and you empower them. They all are empowered. It's not that they all got to run it. It's not the Steve Jobs model where they've got to run everything past me or I'll lop their heads off. They're all empowered. That's how you make it work. So this is one of the cutaways. This is magnesium on top, the salt, and this is the molten antimony. This is Jocelyn, one of my students. She's now got a PhD. This is Steve Chu, who was the energy secretary at the time, who was visiting us. And he came down, he autographed the glove box, and I made sure that we were wearing safety glasses for the picture so I can show the picture in mixed company. So where are we now? We've tested over 1,000 cells, many alloys, many salts. We're working parts of the periodic table people haven't studied. You know, people know a little bit about magnesium, but you know, antimony, bismuth, they don't know much about it. And a number of these are less than $100 a kilowatt hour for the electrodes and the electrolyte. And we do publish. I mean, I don't care about publishing. Why? Because tenure means never having to say you're sorry. So I don't have to publish. But I want to launch the careers of the young people who work with me. And so aim high. So let's publish in the premier journal in the world. That's Nature. This is not Nature Chemistry, Nature Communications, Nature Materials. This is Nature. And it's really tough to get into Nature. I mean, they reject 4 to 5 submissions by return mail. If you send your paper to Nature, set your watch, 48 hours later, you'll have the rejection. It won't even go for the editorial board. This thing got through. And this was an image that Felice Frankel made for us because they want images now. So this is cuvette made of Pyrex. This is liquid mercury, and this is an aqueous solution of sodium chloride in water. And then this is the ferronickel foam. So this would represent a battery that's fully discharged. It's just a cute image. But this is the thing that really makes me excited. It's the stunningly low fade rates. So this is something that's operating at 600 milliamps per square centimeter at 100% depth of discharge. And that's the worst stress test you can give something. Full charge to full discharge. It's not like a Prius between 60 and 40%. 0.0002% per cycle. What does that mean? 10 years of daily cycling, that'd be 3,650 cycles. It would retain 99.4% of its initial capacity. There's no battery can do that. 80% is the normal cutoff, and that would take 305 years, which ought to take care of everybody in this room. And then we started a company, Liquid Metal Battery Corporation. All the sexy names were taken in 2010, and we needed to get it on paper, so there it was. Then we renamed it Ambry because it was invented in Cambridge. So that's the way. And my first investor was Bill Gates. How to meet Bill Gates. I'm Canadian. I wouldn't go to Bill. I'm too polite. He came to me. Why? Because he was watching my chemistry lectures online. MIT decided in 2004 to make all of its material available to the world for free. And so Bill started watching my chemistry lectures on OpenCourseWare. And in August of 2009, I got a email from a woman who said she was his secretary, and he was coming to Boston. He wanted to sit with me for 90 minutes. Would I have time? And I disregarded the email. Because I thought the students had pulled a prank on me. So I didn't answer it. And she wrote me again and said, perhaps you didn't see my email, but Mr. Gates would really like to see you. I said, well, maybe this is real. So he came and we sat and chatted and we talked about distance learning and engineering education, and we started talking about batteries. This was 2009. We had nothing in the way of results. David's early experiments weren't working. But I sketched it on a whiteboard. He says, if you ever decide to spin this out, let me know. I'd be willing to put some money into it. A year later, we approached him. He became our first investor. So why did he become my investor? Not because I gave a talk at a professional society meeting or because I got a DOE grant. It's because I taught freshman chemistry. Everything's nonlinear here, you see. And then we developed a manufacturing facility. This is Phil Giudice, our CEO. That was Deval Patrick, who was the governor of Massachusetts at the time. Developed the robotics to build these things. And this will give you a sense of what has to happen. These are cells, they're 4-inch squares. Eventually they'll be 8-inch squares. And what the company has to do is to move from the lab bench to the marketplace. This is aggregation. And you put that together, it gives you 2 kilowatt hours. It's about the size of a case of beer. And then you put these together and aggregate. So that's 25 kilowatt hours. That's more than enough for a single family home. And then you put packs of those together, and something about on the size of a 53-foot trailer on a truck will give you about 2 megawatt hours. So that's the path forward, and that's a long path. That's why it's not like IT. You and I have an idea for an app. 3 months later, we're rolling in dough. Not this. This is going to take 5 to 10 years. Power electronics, inverters, all of that. I talked to ABB, Siemens, Schneider Electric, General Electric, every one of them. That's how much help. 0. So we did it all ourselves. It's not a problem. We'll just do it ourselves. This is cute. When I came up with the first one, people on the internet were calling it the T1000.
Not like me. The T1000. Advanced prototype.
You mean more advanced than you are?
Yes. A mimetic polyalloy.
What the hell does that mean?
Liquid metal.
Silent, emissions-free, not like a diesel genset, no moving parts. That's good for a long service lifetime. Remotely controlled, in 1 millisecond it can turn from a source to a load. You know, sometimes the remedy for frequency regulation is to dump electricity, not to provide electricity. And we think we're going to get it to the price point. And obviously the first one is way over here, but our cost models indicate we'll be below $500 a kilowatt hour. And the next steps, we continue to make more discovery. I thought I invented a battery. No, it's a battery field. There's this whole concept of liquid metal. There's so much to be discovered. So I said one day, let's abuse this thing. Let's see what happens if we overcharge it. So we're going to charge it. We're going to send the magnesium back. And I said, keep going. And we keep going. And after some time, we start to dissolve antimony, and we develop a second plateau. And the result of that is, this is the discharge and charge of an alloying cell, and this is the same thing on the displacement. So that's 3 times the voltage. These are all both on the same scale. So 3 times the voltage at the same cost. That means your cost just went down by 3x. So I call it Zebra Unchained because it's like the Zebra battery, but it's not sodium-based. It could be lithium-based. It could be. So we're working on that. And that means if you take liquid metal and go to Zebra Unchained, we could be over here. We've got some cells that the capital cost of the electrodes is less than $5 a kilowatt hour on that chemistry. $5 a kilowatt hour. So let me wrap it up. Everybody says make a low temperature battery. I said no, go to high temperature. Got higher energy density. Everybody said build a gigafactory. And I said no, you scale by building fewer, they'll be bigger. Everybody said, hire battery experts. I said, hell no. Hire novices and mentor them. So that's my approach. And this I couldn't resist. I added this. It was a TED Talk the year before I was there, and a woman talked about the mind, and it resonates with me. If we free our minds and we empower our employees, the thing about our mind is we can see the world as it isn't. That's what gives me the ability to invent. It's not to look at what exists. It's to imagine what there isn't there. We can imagine the future and yet remember the past in the same brain. And we can even imagine ourselves being some other person in some other place at some other time. That means we can invent. This is the Bobby Kennedy line. Some men see things as they are and ask why. Others dream things that never were and ask why not. So which are you? Are you up here or are you down here? You choose to be here or here. It's a choice. I used to be up here because I had an engineering education. And I was taught to criticize and analyze. I wasn't taught to build anything. And then I decided, that's no fun. Let's do this. Is that your workplace? Never, ever think outside the box. I say I didn't know there was a box. So this is what I tell my people, the battle cry from Paris: be realistic, ask for the impossible. And sometimes with enough ingenuity, the impossible becomes the inevitable. Thank you.